Ah, doing some woodworking stuff this weekend.
Studying for other tests.
Other tests? You should just be doing calculus.
Physics.
Physics. Who needs that? Who needs physics?
Who uses some of this stuff?
All right. Camera's on. We're recording, and those are a series of rectangles. Partial fractions. All right, so this is there's good news. The good news is this is the last technique of integration that we're going to learn. Yeah. Yes. Seem a little bit excited about that. That's the good news. There's no bad news. I'm not following it up with any bad news. Just saying that this is the last one. So the challenge will be, like I said before, is that on your next test, which is 16th. So we still have a little ways to go, don't we? On your next exam, you'll get an integral, and there won't be any direction other than to find the antiderivative, right? So everything will be on the table, in terms of what you can use. So if you've done your homework, you've kind of seen some integrals. If you use the right method, it can go a little shorter than if you try something else. You might get the same answer, but it might take you longer. So is that a question? Yes.
Is this an integral that you've engineered to incorporate all 5 steps?
No. The test, you mean the test problems?
Yes, sir.
No, I'll keep them within the scope of what the book is asking you to do. All right, partial fractions. So we have a formula on our formula sheet, formula number 17, that, well, that's it right there, but it comes from this one right here. This is one I asked you to memorize a long time ago. Right, that one. That formula is the answer. This is the answer if this is a 1. Okay, but if this is something other than 1, the formula changes quite a little bit. What you have to do is you have to, in front of the arctangent, you have to put 1 over a, and then inside the arctangent, inside this answer right here, you put the variable over a. So if you had something like this, we should automatically be able to just go to 1 over 2 arctangent of x over 2 plus c, because a was 2, right? What if this was 3? What if that was a 3? This would be 1 over square root of 3 arctangent of x over root 3, okay? So just be aware that this formula that we've known kind of extends a little bit if we change that to an a. So use the variable. How do I know use the variable here and a is not the variable?
Because use the one that's represented, it represents x.
du right here.
With respect to x.
Yeah. So if this was an x and x there, then our variable would be x. All right, so can we move on? Everyone okay with that formula? All right, so now before we do partial fractions, before we even get started with it, there are some integrals that we should be able to handle right now. All right, these are things that we should be able to do, and we should be able to do them relatively quick. All right, so let's make sure that we can handle these. And each of these integrals has a specific sort of like format to it that I want us to pay attention to. If we're ever doing an integral where we have a constant divided by a linear expression, okay, 2 is a constant, x minus 4 is a linear expression, right, in x, then we should be able to handle that almost immediately. So how would you integrate that? Just u sub. Basic u sub. So what would the u sub be here? X minus 4 is our u. Du then would be what? dx, okay? So I'm using basic u sub for this, right? This integral would now become, let's see, how about we deal with that 2? Let's pull the 2 out, right? And that becomes, in terms of u, it's 1 over u du, right? And the antiderivative of that would just be natural log. So we get 2 natural log absolute value of u plus c, which would be 2 natural log of x minus 4 plus c. So that's it, right? Now, when I say that here are some integrals that we should be able to do right now, what I mean is, yes, of course I would expect that you can do this. But what I really mean is that you should be able to do that without writing a single thing down, other than the answer. Like you should be to the point where you can just write the answer to this without having to go through all these steps. So let me give you another example next to this one. Negative 4 over x plus 3 dx. Okay, so you know the negative 4 is going to come out, well, hold on, constant over linear, right? So you're like, all right, I'm going to pull the negative 4 out, and then I'm going to have like 1 over u. And what's du going to be? Dx, right? So everything's going to work out where when I rewrite this, it's just going to be 1 over u du. Yes? So I know the antiderivative of that is natural log. So natural log of x plus 3 plus c, done. Yes? Sure? Okay. Constant over linear? Okay. What's different though? See the 2 down here in front of the x? That makes a difference, doesn't it? So right now, if you were to just say, okay, the answer to this is natural log of 2x plus 1, this would be incorrect, right? Because when you take the derivative of this, you have to take derivative of the inside at some point, which would spit a 2 out. And you don't have a 2, right? So what would you need? A 1/2 out in front of this. So it's like if you did the u substitution here, what would du be? If u was this, what would du be? 2 dx, right? And then you'd have to get rid of that dx by dividing both sides by 2. So you'd have a 1/2 in front of your du. Yes?
Isn't the plus 1 also a plus 1/2 though?
Uh-uh. Yeah, when we take the derivative of it. Okay, let's do, well, the next one is another example of this. This is still a constant over linear. Right, constant over linear. So what would u be? If you did a basic u substitution, what would u be? 4 minus 5x. What would the derivative of that be? Negative 5 dx. And you wouldn't want that negative 5 there, so you'd have to divide both sides by negative 5. So you're going to need to put a what out in front of your answer? Negative 1/5, right? So this should just be negative 1/5 natural log of 4 minus 5x. So do you understand what I mean by we should be able to do these, but not have to actually write all that u substitution down? Okay. So constant over linear, thumbs up? Yeah? Okay. So then what's next? How about a constant over repeated linear factor? So this is the same thing as we had before. That's a linear factor, right? That's linear, but squared. So it's repeated, right? So could we do the same basic u substitution? Could u be 2x plus 1? Yes. What would du be? 2 dx, right? So we'd have to get rid of that 2. So we'd have to scale both sides by 1/2. But instead of having 1 over u, we're going to have what? 1 over u squared, right? So again, without rewriting it, I'm going to write it on this one. This would be, I'm going to have to, what do you say I have to scale by? 1/2? Half integral, but this is going to become 1 over u squared du, right? That's what would happen if I did the basic u substitution. Unfortunately, that is not natural log, right? This is the same as 1/2 integral u to the negative 2 du, and then you just use your power rule, right? So if I use my power rule, what would the antiderivative of that be? Yeah, negative u to the negative 1. Negative u to the negative 1 would be the antiderivative of that. So negative 1 over 2u plus c. That would be our antiderivative. And then what was u? Yep, 2x plus 1. Okay, so maybe on this one you have to write a few things down, but you don't want to have to go through the whole procedure. What would change if this was like 2x plus 1 to the 5th? Same thing, right? Except this would be 1 over u to the 5th, this would be u to the negative 5, and then you would have your power rule and you could do it. So constant over linear factor, or linear term, we're good, right? Constant over repeated linear, we should be good. Just a basic u substitution. All right. We move on. Oh, we're not moving on. I did another one. Sorry, I forgot I did another one. Do I need to go through this one? This is the same thing, isn't it? If we did our basic u sub, it would just be x minus 5, right? Derivative of that, du is dx, so we don't have to scale anything. So this would really turn out to be like the integral of 1 over u cubed, right? And then we could handle that? Yes? You could? Okay. Just don't use natural log, right? Because it's third power. Okay, so now something a little different. How about if we have a constant over a quadratic, not linear, we have a constant over a quadratic that is missing the x term. So that quadratic on the bottom has the x squared term, right? And it has a constant term, but it's missing an x term. So how would you handle that one?
I mean, you can use the, what's it called that we did? The trig sub, yeah.
You could use trig sub on that.
That's tangent.
But there's no square root over it, right? No, but you could write it as square root squared.
Oh, yeah, so it'd be x, so square root of x plus
9,
No.
all of that.
Yeah, squared.
Yes, we could do that. We could rewrite that as 1 over the square root of x squared plus 9 squared. We could do that. And then we could use trig sub. But you would be wasting time on a test that would be wasting time. What? I thought you were...
There was like a inverse tangent thing we talked about.
Yeah, it was the first thing I put on the board today, right? The formula for 1 over u squared plus a squared. This is it right here, isn't it? Except it's x instead of u. So this one, without doing any work, is 1/3 tangent inverse of x over 3 plus c. Done. Move on, right? Okay. Now, if you wanted to know where formula 17 came from, right? I'm not going to do it, okay? But if you wanted to know where that formula came from, the formula for that, all you have to do is rewrite this as the square root of u squared plus a squared squared du, like that, and do trig sub. And if you do trig sub on this, then you will actually generate the formula on your own. That's where all the formulas came from. They didn't, I always joke around with my students, like, we didn't find all these formulas on the back of like a tablet somewhere near a burning bush or anything, you know? Like, it wasn't like all the physics formulas and math formulas, right? Like, everything we had to generate ourselves. So all those formulas you see are things that have been generated. So if you want to generate it, this is the way you do it. We're not going to. We're just going to use the formula. All right. Question. I have a question for you on this one. What if that was x squared minus 9? So we can't use that formula anymore because the formula only works if you had u squared plus a squared. So on your formula sheets, do you have a formula that handles like u squared minus a squared on the bottom?
Yes.
Is it under a square root or is it by itself?
By itself.
Can I see it?
Number 20.
Number 20. Ah, so you'd use formula number 20 for this one. Okay? So I'm going to say this would be formula 20. Well, go ahead and you tell me what the answer is, okay? Because I don't have that one memorized. Dx, forgot my dx here. So according to that, what is it? Is it like 1 over 2a? What? 1 over 2a, so what is a for us? 3. So this is going to be 1 over 2 times 3. I'll put 6 on the next line. Natural log. Is it a fraction in here? X minus a over x plus a? Plus c. Okay, so that would be it. It'd be 1/6 the natural log of x minus 3 over x plus 3. All right? That would be the answer, going off of formula 20. Okay, one more of these. What if I did this? Can you still use formula 20? Really, 19? It has not. That's ridiculous. Because look, all you have to do is this. Take a negative out of the bottom. They shouldn't give you formula 19. Right, this is the same expression, isn't it? Just factor a negative. That's a negative out here. -1, boom. Okay, so that -1 could go back through here and give you that. So if you pull the -1 out, you're here, and then you use formula 20 again. But they give you a formula 19. I don't know why they do that. 19 and 20 are the same thing. It's just not the same formula, but they do the same thing. So you should be able to handle, right? Do you all see that if you have a constant over a quadratic that's missing the x term, there's no other scenario that you could run into. Like this covers it all. Those formulas 17, 19, and 20 should cover it all. Can anyone think of a quadratic, a constant over quadratic that's missing an x term that you couldn't do with those?
Square root of x plus 9.
Square root of x.
1 over square root of x plus 9.
Square root of x plus 9? It's not a quadratic. I'm saying
Oh.
constant over a quadratic missing the x term. What if it had a constant with the x squared? Good. Okay, so let's try that. How about 4x squared plus 1? That's a good question. So what would you do here? Pull a fourth out. Pull 1/4 out. So that's not a 4. That's a 2. Okay, pull a 4 out of the denominator. If you factor a 4 out of the denominator, you would have what here? X squared plus, pull the 4 out of that, that's 1/4 dx. And now you can. See that? And it wouldn't matter if that was minus or if they were flipped over, that would change the formula. But as far as the number in front, you could just always pull that out. Agreed? Anyone have another idea of something try and trip me up here? That was good. I'm glad you brought that up. So we can handle it then? Can we move on?
So what if the second term also has an x?
Then, but the whole thing is we can handle it if it's a quadratic, if it's missing an x term.
Oh, I'm sorry.
Yeah, we have to be. If you want me to put the x term in, well, then that's a different story.
Okay.
We're going there, okay? We're headed there. So let's just review. Constant over linear, we're good. Constant over repeated linear, we're good. Constant over quadratic missing an x term, we're good. Okay. Constant over an irreducible quadratic. What does irreducible mean? Can't factor it. So look at that quadratic down there. Look at that quadratic. It's not factorable. You cannot break this up into like 2 sets of parentheses, x plus something times x. You know what I mean? It's not factorable. So how can we handle this? Because at this point right now, from here on out, this is not something that I would have expected you would know how to do. Okay? Now we're starting to come up with like ways to do this. Everything up to this point is something should have been within fair rules of what we've seen. But now, what if we have something like this? So anyone have any ideas on how we could go about this? Who's that? Complete the square. Now, why? What makes you think to do that?
Just in the past of all my other math courses, usually when you have something that's intractable, you either use complete the square or quadratic formula.
Yeah. So here, completing the square is just something we know we can try, right? So let's try it, right? Let's go for it. All right. So for us here, if we complete the square, we talked about this last class, didn't we? We have to be real careful with completing the square on things. You know what? Yeah, let's just do it. So to complete the square, we make sure there's a 1 here, which there is, right? Then we take half of this number, which happens to be 1, and we square it, which is still 1, and then we add and subtract it. So this is where I will add 1 and take it away, like that. Okay, right? And now, what do the first 3 terms guarantee factor to be? That's going to be x plus something squared. What is it? X plus 1. Right? X plus 1. And then what do we still have over here? Plus 16. Okay, so now let's rewrite the integral. This integral becomes 1 over x plus 1 squared plus 16 dx. Right? So what have we gained here? Well, I mean, we just rewrote it, right? I mean, we didn't change the problem. We just rewrote it. It just looks different. But if you squint your eyes just enough, right?
X plus 1.
Yeah, like the x plus 1 is essentially like a u, right? Like in a basic u substitution, just a basic u sub. If I did this, u is x plus 1, what's du? Dx, right? So that would allow me to switch this problem right now over directly to 1 over, what? U squared plus 16, dx is du. And where are we now? Constant over quadratic missing the u term, right? So now we can actually use formula 17, right? We can use formula 17 now.
Isn't that also inverse tangent though?
That is formula 17. Wait, it is 17, right? It is 17, yeah. That is 17. So what would this be according to formula 17? 1 over a, arctangent, so 1 over 4, right? 1 over 4, arctangent of u over 4 plus c. And we would have one more step. We'd have to replace u with x plus 1. Boom, we're there. Should this work for every irreducible quadratic? Well, can you complete the square of any quadratic? You can. And when you complete the square on any quadratic, you're always going to get something squared. And then over here, you're either going to have plus some number, right? Or you're going to have minus some number, right? One of those is going to happen when you complete the square. If you have plus, then you're going to be able to use formula 17. If you have minus, you're going to be able to use formula 20 or 19, whichever way they appear in the problem. Does that make sense? So we've got this base covered now, right? Constant over irreducible quadratic, we should be able to complete the square and go to town with our formulas. Maybe a little basic u substitution in there, but we should be able to handle it. So constant over linear, constant over repeated linear, constant over quadratic missing x term, we're good. Constant over irreducible quadratic, we're in business, right? Okay. Y'all feeling okay about this so far? Was that no? Did you say no? All right. Yes. Yes. The question was, if we had the previous problem, if we would have had a coefficient right here, like 3, let's say that was a 3, right? Then when I complete the square, I can't have the 3 there, right? I have to get it out of there. So I would have started by pulling a 1/3 out. Now, that would have made all these fractions and it would have sucked, but I mean, that's life, right? Okay? But you could do it, right? Like it would go. All right. Up to this, every single problem I've done, we've had constant on top, haven't we? Constant, constant, constant linear, constant linear, constant repeated linear, constant repeated linear, constant quadratic. And finally, on formula, or on 7, we have a linear expression over a quadratic. And the quadratic is irreducible.
So imagine you would pull the 4 out of everything first and then complete the square. And then that would probably give you an x minus 1 somewhere, which then you most likely cancel with the top, making it 1 over the complete, or the square that's complete.
Wait, say that again?
So I'm speculating here that you can pull the 4 out, and then after you pull the 4 out, you complete the square on it, and then after you complete the square, somewhere in that square, it would give you x minus 1, which then you could use to cancel with the top, making the top turn into.
Why do you assume that you would have an x minus 1 in the completing of the square?
Just based off derivatives.
Okay, so you're hoping that that's what would happen?
Yes.
Okay.
It looks like we need to use U sub first before we complete the square.
Why U sub?
Because we have a linear in the numerator, and we need to be able to get rid of that somehow to convert it to a constant. And one way to do that would be to do U sub first before you complete the square.
Let me see, what would U sub get us? Let's just talk about U sub for a second. If I did U sub, what's U?
Be 4x.
The whole thing? Okay, so you're not even looking at completing the square right now, right?
No.
Okay, so let's just follow this path for a second, see what happens here. Du would be 8x minus 4, wouldn't it?
Yeah.
Dx, right? And isn't with basic U substitution, aren't you supposed to see something in its derivative? And this right here, I do not think I see that. I see x minus 1 dx, but I don't see 8x minus 4 dx. Would you agree? I'm not sure if that's what you were wanting me to do.
Yes,
like,
it was.
so you could maybe rewrite this as like 1 over u and do like a natural log or something? No?
No, there is more to it. It's
Okay.
Something like. Never mind.
Well, this is the way I'm going to go. I just want to make sure we all understand that like basic U substitution is not going to work here. And I'm also going to say this. I'm going to put an asterisk right here. If you go to the lab and you get help, or you go to your friend who's already taken this class, or you go to some other tutor, or if you've learned this before in the past, whatever, the way I'm going to show you to do this is probably going to be different than any of the ways that you will see it from anyone else. And it's only because I don't know, it just makes sense to me this way, and I think there's little things inside of what I'm about to do that are more beneficial later to you in terms of the way you look at a problem. Because there's like a more systematic approach that I could show you, but it takes away like the critical thinking part that I think is important. All right? Yes?
You take that x to the x minus 1 and peel it off to the side, giving you 1 over that whatever the irreducible quadratic, and then pull out a 4 and start completing the square.
Okay, so I think your question is this. Can we just rewrite this as x minus 1 and then just peel that thing off 1 over the quadratic like this? We could, like if that was the problem, we could integrate it. The problem is it's attached through multiplication to this. So for the same reason that like when we're integrating like x times sine x, you can't just do them individually, right? You can't just say, oh, the antiderivative of that's 1/2 x squared, and the antiderivative of that's negative cosine. Just multiply those two answers. Can't do that here either. We can't peel and do that, and then that separately and put them together. That would make calculus 2 a lot easier, wouldn't it? I mean, if we could do that, we can't though. What is it about it being linear up here that prevents us from completing the square and doing what we did before? Because in the previous problem, didn't we just complete the square? Yes? And then we had like 1 over u squared plus a squared, and we were able to use a formula. The key was that the top would have been 1, right? Or a constant. In the formula 17 or 19 or 20, it's a constant up top, right? Here, we have a variable up top for the first time. So the basic the formulas will not work. Does that make sense, that the formulas won't work? You all right?
Is there a way to like take that bottom one and like divide it by x minus 1 and get some fraction?
Take
right?
the bottom one and divide
So
it by...
taking the bottom thing, right?
Mhm.
If we wrote it as in terms of x minus 1 times something,
But it's not, because it's irreducible. If it were reducible, well, I mean, it's something, but it won't be a polynomial. I think what you're suggesting is taking that and dividing it by x minus 1.
Yeah.
And that way you could figure out that this is really like x minus 1 times something, right? This right here is not going to be a polynomial. It's going to be some other sort of rational function. It's going to be weird. Okay, so are y'all ready? I think I'm going to show you now. I just want to make sure everyone understands we're kind of stuck right now. Yes? Okay. So here's the way I view this problem. If the numerator, right? If the numerator was 8x minus 4, we would be in business. Do you all agree? If the numerator was 8x minus 4, we would be in business. Because then I'd have u, and then du would be up top, and we'd be done, right? So we're going to make it 8x minus 4. Okay? Here's how we're going to do it. First thing I'm going to do is I'm going to multiply by 1. So I'm taking the original problem right now, and I'm multiplying by 1. Now the 1 I'm using is 8 over 8. Now why am I using 8? Because I want 8x, right? I want 8x. So now let's pass the 8 through the numerator and leave the 1/8 on the outside. So do you all agree that I have not changed the problem? Like, this is the same problem. Yes? Y'all agree? I don't hear like a resounding yes. I have not changed the problem? Same problem? Okay. I wanted it to be 8x minus 4. Right now it's 8x minus 8. I'm close. I'm close, right? So the next thing I'm going to do, I need it to be what? Minus 4. So guess what? I'm going to put it there. And then I'm going to undo it. Okay? Now what was still there though? Hold on. I still had minus 8. Now I realize that some of you are sitting there going, like, couldn't you just rewrite that as 8x minus 4 minus 4? Couldn't I?
yeah.
I could, right? But sometimes these are going to be fractions and stuff, so it's not obvious that you can rewrite it. So what I'm telling you is if I'm trying to get it to become 8x minus 4, the first thing I did was made the 8 happen. Then I put what I needed here, minus 4 plus 4, because I needed the minus 4, right? Yes? Okay. Do y'all see where I'm headed with this? Okay, keep going here. I have 1/8 integral. Let's see, up top I have 8x minus 4, right? That's these two. And then let's just put those two together. So what's those two together? Minus 4. Okay, so I have minus 4. And then over 4x squared minus 4x plus 3 dx. So I've just found a way of rewriting the problem, right? Big deal. But do you see what I can do now? Do you all see it? I'm going to split this into 2 integrals now. Do y'all see that? I'm going to split it at the red. I'm going to do this over this plus this over this. Yeah? So let's see what happens. I have 1/8 integral 8x minus 4 over 4x squared minus 4x plus 3 dx. And then my new integral is going to be what? I have this minus 4 here, right? And I do have a 1/8 out front. So how about we make that minus a half integral 1 over x to the 4th minus 4x plus 3 dx. This would be a good time for you to ask any questions about what I've just done. Do y'all see the split? This over this with the 1/8 out front. this over this with the 1/8 out front, and then I pulled the -4 out. Yes? Yes?
So why didn't I just like plug in the u and the du and put the -4 by the du,
Wait, why didn't we do what?
which is going to be -4 u to the power -1 du?
You're saying back at this step right here.
Yeah.
Why didn't we just write this as
U and du.
u
Mm-hmm.
and then du? Because this is not du.
It's -4 du.
No, this is not multiplication. This is right? Yeah, that's subtraction.
Yeah.
But you can do it here. This is u du, right? This is u du right there. Perfect, exactly what we wanted, right? So we made it look like we wanted it to look, but we still have one integral to deal with now, right? But what's good about that integral? It's a constant over an irreducible quadratic. And so I can complete the square on this one. See that? Now I'm back to the previous idea. Yes, what we just did before you have to do now within this problem, but this is the way we can do it. It's pretty nice, isn't it? So this one's just going to become 1/8 natural log of 4x squared minus 4x plus 3. So I'm not even showing this work, because we already knew that when we did a basic u substitution, this was u, that was du, so that's 1 over u, antiderivative 1 over u is natural log of u. Yes? That's what that is. So I'm done with the integration on that one. On this one, I've got to complete the square, right? So we're going to start by pulling that 4 out. So we'll pull the 4 out. And you know what? Since this is going to be a lot of work, let's go ahead and just separate it, and we'll just go do this integral over here. So I'm pulling a 4 out, so it's going to become a minus 1/8, right? Integral 1 over x squared what? Minus x plus 3/4 dx. So that's just pulling this 4 out of the bottom. And now we get to complete the square on that one. So maybe I'll do a little quick completing of the square here. I'm taking x squared minus x, and then what's the number I'm going to add and subtract? So we're taking this number right here, right? -1. We're dividing it by 2, so -1/2. We're squaring it, so 1/4. So I'm going to add a 4th and subtract a 4th, and then what do we still have there? Plus 3/4, right? So these three become what? Something squared? X minus 1/2 squared. And then these two together become 1/2. So we're at -1/8 integral of 1 over x minus 1/2 squared plus 1/2 dx. We haven't even started partial fractions, right? We haven't even started it yet. We're just making sure we can handle these types of things, because these are the things that are going to show up when we do partial fraction decomposition. These are the types of integrals we'll need to be able to handle. So we've got to make sure we can do them before we actually try and start a method that's going to get us to these. All right. Okay? So for this, we're going to use what? Formula 17. This is basically like 1 over u squared plus a squared. U here is x minus 1/2. And so if I did a substitution like u du, I don't have to worry about scaling anything. So let's pull, where are my sticks? Let's pull these sticks. Let's see. Stephen, Jacob, Jordan. Did I call y'all last time? Max, Tatum. Last time did I call y'all? Yeah, I don't think. Jace, did I call you last time? Do you remember? Chris, did I call you last time? Okay, y'all, no, I'm just mixing y'all up again then. Martin. Okay, Martin's up. So Martin, I was here, I said I needed formula 17. You agree with that? So can you tell me what this is written out with formula 17?
So
Negative 1/8 out here?
multiply by 1 over a being 1/4. So 1 over
Hold on.
is 4.
So 1 over a, the formula is 1 over a, and you're saying a is 1/4? Careful. This is a squared, right? A squared is a half. So you take the square root, and that means 1 over root 2 is 8. With me? Everyone with me? This is a squared, so a is 1 over root 2. I'll clean it up later. Yes?
Yeah.
Okay. Keep going.
Tangent.
Arctangent. Mm-hmm.
U, or x minus 1/2.
X minus a half, right? That's our u, basically, over
A, which is
1 over root 2. That ain't pretty, but that's it, okay? That ain't pretty, but that's it. So this is this integral right here, right? So it's time to put this back in over here. Now I'm going to clean this up. I'm going to flip that. That fraction is going to come up and I have a root 2 on top. And that's going to be over here with this 1/8. So I've got something like negative root 2 over 8 arctangent of, and then, I don't know, I mean, this is kind of up to you on how you want to write this. You can just put this, I don't mind, or you can flip the root 2 up, and the root 2 can go out in front of this thing. I think I'm going to do it that way. I'm going to write it root 2, and then x minus a half plus c. And we're done. I mean, who would think that to find the antiderivative of a rational function like that, it would require logarithms and inverse tangent functions, right? So if I take the derivative of this, right? Take derivative of this, go through all that crap in Cal 1, I should be left with that at the end. All right, questions? Anything before we move on? Do I need to recap anything or review
Can
anything?
you remind me again how you got the square root of 2? Like, why is it 1 over square root of 2 over 2? Sorry, 1 over square root of 2.
1 over square root 2. Okay, so this right here
Yeah.
looks like the formula 1 over u squared plus a squared.
Right.
If this was a 4, you'd say a is 2, right?
Right.
If this was a 9, you'd say a is 3. But this is a half, so you have to take square root of it, right? And so that's what I did up there. Like I said, if you go to a tutor, there's probably going to be another way you could go and do this problem. I know there is, and it's slightly shorter. And look, if you wind up liking that, you're not going to hurt my feelings, okay? But like I said, I think that this is more in line with just being really clever about how you want, that whole thing of making it happen, making it be what you wanted it to be is just a higher level of thinking. Yes?
So how can you do the same thing for the u? Like square root it? We just put
It was squared.
Oh,
This is u squared, right? Plus a squared. This just isn't written as a squared, right? So if I want to rewrite that as something squared, I have to rewrite it as 1 over root 2 squared. And that's 1/2 still, right? That's 1/2. So now it's u squared plus a squared.
so that's why we just plug it in the log one?
Well, that's the formula. The formula. You have to look at the formula. The formula is 1 over a arctan of u over a. No? Okay, you want to see what's... Oh, yes, sorry, I saw your hand, forgot. Can you use this? What do you mean whenever?
Like, if we have a problem like similar to that, can we just keep using that?
Well, in completing the square, you always want to use this, right? Are you asking me, like, can you just always use that anytime, whenever?
Oh, because I've never used it.
For completing the square? Were you here last time?
No, I took
You don't have to explain it. You weren't here last time, right? Okay, so I went through it all, didn't I? We had a whole big, like, come to you-know-who discussion about completing the square. So that was recorded and posted for you to watch if you missed class. Yeah, so if you're not familiar with this, you should go back and watch it. Right, we did go through that, right? I went through and said, okay, all right. All right. Okay, so how about a linear expression over a repeated irreducible quadratic? So just like the previous one, we have a linear on top this time, right? Just like the previous one. This time the bottom is a quadratic that's irreducible. X squared plus 1 cannot be factored, but it's repeated. It's repeated. Well, how did we do the last one? U sub? U sub, and then we started to try and get clever with it, right? Okay, so let's try that. If we were to let u be equal to x squared plus 1, du is what? 2x dx. Now, I would love to have a 2x dx up there. I don't have a 2x dx. I have x plus 1, right? So let's make it 2x, right? Luis, you understand what I'm saying? I want the numerator to be just 2x. Right now it's x plus 1. So can you help me make it 2x?
Yeah, put a 1 in front, but it's a 1 leaving 2 over 2.
Okay, so you want me to put 2 over 2 out front. You're using 2 because you need 2x, right? Okay. All right, then you want me to do what?
Oh, okay, you have to split the top and the bottom, right?
We will, not yet. Let's use the 2, right? We need to use the 2.
Okay, you're going to distribute.
Okay, so the 2 is going to go through both terms, right? On top, and I still have a 1/2 out front. So 2x plus 2 over x squared plus 1 squared dx. Now you want it to just be 2x, right? But you actually have it, right? Like right now, you could split this, couldn't you? You could just split it right now. And it'll become 2 integrals. The first integral will be 1/2 integral 2x over x squared plus 1 squared dx. Now, why do we like this one? Why is this okay? This is just basic u substitution. U is this, the derivative is right up top. So this is just going to turn into 1 over u squared with a basic u sub. Yeah? Now, the other integral is Gabriel?
That'll turn into 1 over 2, 2 over x squared plus 1 squared.
Okay, and so that 2.5, can I go ahead and clean that now? Just pull that 2 out. Is that all right?
Yep.
So integral 1 over and then just x squared plus 1 squared dx, yes? We happy or not happy, but we okay up to this point? So this one's check. I'm going to say check that we could do. We're not even going to think about that one anymore. All right? We're going to think about this one. Okay, so all my focus and my attention right now is on this integral right here. God, I wish that squared wasn't there on the outside, right? right? If this squared wasn't here, then we'd be where? Formula 17, arctan, right? we'd be there, right? But it's squared. If we expand it out, we're going to have 1 over a 4th degree polynomial, right? And we can't split that up into separate pieces because it's one term on top, multiple terms on the bottom.
Seems like you could do U sub again.
U sub?
And make it look like it was.
Well, if I do U sub again, I need the derivative to be 2x, right? And the problem is I don't even have an x up here, right? So you cannot, this is real important. You cannot put 2x over 2x here and then push a 2x in. You can put a number over a number and push a number in, but you can't put a variable out here and push a variable top and, you can't. Because variables don't go in and out of integrals, only constants do. All right, trig sub, yeah, I mean, sorry. Sorry, I hate to be the bearer of bad news here, but you have to rewrite that like this. To the fourth, because you're going to first rewrite this as a square root of something, right? And then you have to get it to become squared at the end. So square root of this to the fourth would be the same as that squared. Do you all agree? And now you go to trig sub. This is no joke, right? I mean, this is no joke, this stuff right here. Everything, we're bringing everything out, right? What's that movie, The Professional? Have y'all seen that one? The Professional, The Hitman, old movie. No? Who's seen The Professional? Do you remember the name of the guy, the police officer? Like what his name is, the actor? Yeah, well, yeah, I guess so. The main police guy. God, what's his name? Anyway, there's a scene at the end where they've got the guy they're trying to catch cornered in a building, and he says, tells the other officer, he's like, bring everyone. And he's like, who do you want me to call? He's like, everyone. So, I'm thinking about like, how do we do these problems? Like, what do you use? Everything, like just everything. Okay, everything's on the table. There's nothing off the table now. Not a good analogy, but I don't care. All right, so what do we do? Trig sub, what's our trig sub? We're going to replace what with what here? X becomes tan theta, a tan theta. Now, we do have to be careful because it's a, right? What's a for us here? 1. So it's just x is tan theta. I don't know. I sit here and I ask myself sometimes, how far away am I now from when I was on that end learning this for the first time? Like, I wonder, because the way I talk about it, I think, I don't know how it comes across to you, but I'm just like, it blows my mind that I gave a quiz over this last class and majority of you could not do that, right? Could not tell me what this is. And here we are, one class later, and this is one tiny piece of a bigger problem. Do you see that? Like, it's hard in the beginning of a class like this to kind of like explain what I mean by this thing builds so quickly on itself, right? So I hope I've done that, like tried to like tell you how fast it comes and how quickly it builds. There's no time to try and I'll take a day off or take 2 days off or not do my homework. All right, I'm yapping up here. So what does the square root of x squared plus 1 become? That's going to become secant theta. And then what does dx become? Secant squared theta. D theta. I took off on some of your quizzes for not putting d theta. All right, we rewrite the integral. And it becomes Octavio, sorry. So just help me rewrite this. 1 over, what is all this?
It's going to be tan tangent squared theta secant.
No, this right here is the square root, this right here, right?
Oh yeah.
Okay, so that's secant
Secant theta.
to the fourth, right? So we have 1 over secant to the fourth. Octavio, are we done? What else needs to be here?
Dx.
Dx, and dx is
Secant squared.
secant squared theta. God, I love this shit so much. This is just crazy. This is going to become 1 over secant squared. 1 over secant squared is cosine squared, and how do we deal with cosine squared? Power reduce. Right? This is 1 over secant squared theta. I mean, to me, this is just beautiful. I mean, I realize it sucks, you know, when you're learning it, it sucks, but it's just so amazing to me how this all just. We know how to do that, right? Oh, wait, no, someone's going to tell me how to do this. David's going to tell me how to do this. David.
It turns into a 1 plus cosine 2 theta.
And there's a constant there, isn't there, also? Like in the formula, it's not just 1 plus, right?
Oh, it's the
You're at the right formula, you're just missing a number.
constant. Oh, the fourth on the outside.
Half,
Half.
right? That right there is going to become 1/2. 1 plus cosine 2 theta. You're missing the half.
Didn't it get canceled out a while ago?
No? No, the formula for this will generate a half.
Yeah, my bad. Yeah, for sure.
I don't even remember where we were from before. It's way somewhere else. I have to go back to it later. Okay, now we can integrate this, right? So David, I'm going to keep you going here. We're ready for antiderivative now, right?
Yes, so it's going to be theta plus
Theta.
1/2 cosine 2 theta.
Good. Plus 1/2
cosine 2 theta.
anti.
Oh, sine.
Yeah,
Sine.
okay, yep.
My bad. Do that all the time. D theta. Plus C.
Plus C, yeah. And we could do the plus C later, because remember we had other stuff from the beginning of the problem? All right, and we've done this before. We know that we can't deal with that, right? We have to turn that one into that identity. So we've done that probably 30 times now, like homework and in class. Sine theta, cosine theta. And the 2 that comes out of that formula cancels with the 1/2. All right. Stephen? It was your idea to do this, so I'm going to take you off the hook because you told us exactly what we were supposed to do. Edward, unless you want to go, Stephen, I don't care.
I don't know, it doesn't matter, we're just finishing it up.
Yeah, so how would we finish this up?
The theta would become tan inverse x.
Okay, so you're working off of,
The x equals tan.
okay, so off of the x equals tan theta from way before when we did our trig sub, to get the theta, you did arctan? Both sides? Okay, so arctangent of x equals theta. So check, I'm good with that. This will become that. And then what about this stuff?
You would have to finish up the triangle.
Okay, so reference triangle, right? So we got the reference triangle, theta. That's all I wanted to hear. X, 1, square root, x squared plus 1. Hey, there it is. Right, so this triangle is coming off of that information right there. Tangent is opposite over adjacent. Opposite over adjacent is x. So sine is this over this. Cosine is this over this. Okay, we're almost there. How exciting. Okay, 1/2. I'm going to distribute the 1/2 through here when I write this out. So 1/2 theta, and you said theta was arctangent of x. And then the 1/2 is going to come out here, plus 1/2 sine theta off that triangle is 1 over the square root of x squared plus 1 times cosine of theta is adjacent over hypotenuse, 1 over square root of x squared plus 1